100 meters underground, inside a ring 27 kilometers around, magnets have been chilled to a fraction of a degree above absolute zero, colder than the empty space between the stars. And in the summer of 2026, they shut the whole thing down on purpose, at the exact moment something in the data had started to refuse to behave. Why would physicists power down the most powerful machine ever built precisely when its numbers had begun breaking the rules? And what did they see that the rest of us didn't? For one summer in 2012, the map of matter looked finished. On the 4th of July that year, two vast detectors at CERN called ATLAS and CMS announced the Higgs boson, the last missing piece of the theory physicists call the Standard Model. With it, every particle the theory demanded had finally been found and measured, and the book of matter appeared to close. That is what makes the present moment so strange. When a picture is complete, a fresh crack in it is not a gap waiting to be filled. It is something the picture was never supposed to allow. This channel follows the real published research out of CERN, not the hype, and something has just been confirmed there. So subscribe and stay with this one, because what came next was not a rumor or a press release. It came from a paper with named authors and a date. That crack lives inside a single decay. When a particle called a B meson falls apart, one particular version of the process, written as a neutral B meson going to a K star and then to a muon and its antiparticle, keeps happening in a way the Standard Model cannot quite reproduce. In December 2025, the LHCb collaboration submitted a comprehensive analysis of exactly this decay, published the following year in Physical Review Letters. The physicists William Barter and Mark Smith are among those who put their names to the result. The mismatch between what the theory predicts and what the detector actually sees sits at about 4 sigma. In plain terms, that is roughly a 1 in 16,000 chance the discrepancy is a statistical accident. It is not yet enough to claim a discovery. That line sits higher. But it is far too stubborn to wave away as noise. To see why this decay matters so much, you have to know what kind of decay it is. Physicists call it a penguin. The quark at its heart is attempting a transition that the Standard Model forbids as a direct, single step. It is allowed to happen only through a fleeting quantum loop, a detour in which particles flicker into existence and vanish again too fast to observe. That detour is precisely the trap. If some new undiscovered particle exists, it can slip into the loop and nudge the rate of the decay, leaving a fingerprint without ever appearing directly. And there are two leading suspects for what that hidden particle might be. One is a leptoquark, a proposed particle that would bridge quarks and leptons. The other is a heavy cousin of the Z boson. For now, both are interpretations, not sightings. There is a reason this refuses to die. No single one of these B decay measurements crosses the discovery line on its own. But when you combine dozens of them, the rates, the angles at which the particles fly apart, related decays measured alongside, they all lean the same way, and taken together the pattern reaches roughly 5 sigma. That sounds decisive, and it is the catch at the same time, because that number leans on a notoriously hard theoretical calculation. Inflate the uncertainty in that calculation, and the significance can fall to barely 2 sigma. And before anyone reaches for new physics, there is an honest, boring suspect to rule out first: loops of charm quarks, sometimes called charming penguins, whose contribution is genuinely difficult to compute and could in principle fake the whole effect. Recent calculations suggest they struggle to account for all of it. But the question is not settled. To understand why physicists trust a crack that has not yet been proven, go back 50 years to a moment that reads almost exactly like this one. In 1973, Two young physicists in Kyoto, Makoto Kobayashi and Toshihide Masukawa, were wrestling with why matter and antimatter behave differently at all. The known particles could not produce that difference. So they made an extraordinary claim: there had to exist a whole third generation of quarks, particles nobody had ever seen, for which no experiment had a shred of evidence. And the asymmetry between matter and antimatter was written into the way those unseen particles mixed. At the time, there was no reason to believe them beyond the mathematics itself, and for years the idea sat on the shelf. An elegant answer to a question most people were not convinced needed one. The quarks were found one by one over the following decades, and the deeper prediction, the specific pattern of matter-antimatter asymmetry their theory demanded, was finally confirmed in 2001 by two experiments built for the purpose, Babar and Bell. In 2008, Kobayashi and Masukawa were given the Nobel Prize. The lesson physicists took from it is not subtle. The prediction the field ignored longest was the one hiding an entire missing generation of the universe. That is the template sitting behind every cautious sentence about today's anomaly. And yet, caution cuts both ways, because physics has spent the last few years publicly killing its own discoveries. The most famous version of this very crack has already closed once. For years, headlines described an anomaly in which electrons and muons seem to behave differently in these B decays, a violation of one of the Standard Model's quiet assumptions. Then in 2022, LHCb measured it again with better data, and the effect landed almost exactly on the value the theory predicted. It simply evaporated. The same year brought a louder example. An experiment at Fermilab weighed the W boson and found it about 7 sigma too heavy, a result that, if real, would have demanded new physics outright. By 2024, a measurement from the CMS experiment had pulled the number back into line, and the revolution was quietly withdrawn. That is exactly why the surviving crack is worth attention. In a field that demolishes its own headlines this readily, the anomalies that live through the gauntlet are the ones worth trusting. It is worth pausing on the machine that produces all of this. To make the collisions happen, the ring's magnets are cooled to 1.9 Kelvin, a hair above absolute zero. Inside it, bunches of protons cross paths as often as 40 million times a second, and at the points where they meet, matter can briefly reach 100,000 times the temperature at the center of the Sun. The protons themselves travel at 99.999991% of the speed of light, fast enough that time for them, genuinely runs slower than it does for us. And when two of them collide head-on, their energy does not simply scatter. It condenses into new particles that were not there before, mass conjured directly out of motion, Easterloo MC run in reverse. For a fraction of an instant, each collision is a small flash of the universe, as it was moments after the Big Bang. And that early universe is where the stakes finally reach back to us. In 2025, the same LHCb experiment watched matter and antimatter break the rules differently inside a baryon, the family of heavier particles to which the proton and neutron belong, and it was the first time that difference had ever been seen in this class of particle. The measurement crossed the 5 sigma line cleanly. Why should you care about an asymmetry in an exotic decay? Because that asymmetry is the reason there is anything at all. If matter and antimatter had emerged from the Big Bang in perfect balance, they would have annihilated one another completely and left a universe of nothing but light. No galaxies, no planets, no one to measure any of it. Something tipped the scales toward matter. And here is the uncomfortable part. The amount of rule breaking the Standard Model itself permits is far too small to explain why we are here. Something is missing from the story. That is what makes the leptoquark possibility so much larger than one more particle. If the thing hiding in that loop really is a leptoquark, then quarks and leptons, the two halves of matter that the standard model keeps strictly apart, would secretly be two faces of the same thing, joined beneath the theory we already have. A door like that is not one you find and leave. On the 29th of June 2026, CERN switched the collider off on purpose and began tearing out more than a kilometer of accelerator, rebuilding it to pack particles far more densely and to produce collisions at a far higher rate, the intensity it would take to push through the door rather than merely glimpse it. So the door is open a crack. The global picture still leans toward something new in these decays. Nothing has crossed the discovery line on its own, and roughly 3 times as much data is already recorded and waiting to be read. If you want to be here when it is, subscribe, leave a comment telling us which of these threads you want followed as the numbers come in, and a like genuinely helps the argument reach people patient enough to sit through all of it. For now, 27 kilometers of collider lie powered down and half dismantled in the dark, an unfinished sentence waiting for the lights to come back on around 2030.